All right. Yeah, thanks a lot, everyone, for coming, despite the completely uninformative title. I promise I'll tell you soon what these counterexamples are about. But I do want to give sort of a strange talk today, in that all I'm really going to do is tell you a single construction that uses some very classical geometry that I think these days is mostly used by people in complex dynamics. But I want to show how this very classical stuff also can give you some answers to some other more recent questions related to derived categories and birational geometry. So before I get started, let me just say a couple words about just properties of the derived category as an invariant of the variety. So when I say the derived category, I'm always going to be talking about the bounded derived category of coherent sheaves. All my varieties are going to be smooth and projective, and let's just say over C to stay out of trouble. But almost everything I say is OK on any uncountable field. So the first thing to know is that the derived category doesn't uniquely determine the variety in general. I apologize to the experts who already know my first slide here. So maybe the most basic example of this is that an abelian variety and its dual are, in general, not isomorphic, but they are derived equivalent. And this is pointed out by Mukai, I guess. Another example is that if you have two smooth threefolds that are related by a standard flop, even though in general they won't be isomorphic, they do have equivalent derived categories. This is Bondal and Orlov. And this is the property that I'm going to use later in the talk today. OK, so I think there are many, many questions you could ask about just how strong an invariant is the derived category. What else does it tell you? And of course, it has quite a lot of information. And it does tell you some other familiar invariants. For example, it determines the dimension of x and the numerical dimension of x, or even the whole pluricanonical ring. All right, but the question I want to talk about today is this. This was asked by Kawamata. Suppose we're given a smooth projective x. We want to know how many other varieties are there that have the same derived category as x. How many Fourier-Mukai partners is the other word here. And the question in particular is that number always finite? Up to isomorphism, of course. Right, and the conjecture was that, yeah, no matter what x is, you always only see finitely many other varieties with the same derived category. OK, and the answer in quite a few cases is yes. So let me just tell you some results in this direction. All right, the first maybe is that if x is phono or kx is ample, then everything is OK. Because in that case, by the Bondal-Orlov reconstruction theorem, in fact, there are no y's other than x itself. Maybe next we can say curves. It's also true. I guess for anything except elliptic curves, that's covered by this. And elliptic curves are also fine. This is also proved for surfaces. And this one is, I think, one of the harder cases where this is true. It was originally proved by Bridgeland and Machocha in the case that x is minimal. And then this was extended by Kawamata to all surfaces. But already in dimension 2, you start to see interesting things happen. The number of Fourier-Mukai partners is, I mean, it can be as large as you want. It can be bigger than any finite number. But no matter what x is, there's always only finitely many. All right, what am I forgetting here? OK, it's true for abelian varieties. I guess this has sort of two parts. So Orlov showed that for a given abelian variety, the set of other abelian varieties with the same derived category is always finite, and you can more or less get a handle on what they are. And then I guess as a second part, Favero showed that if you're derived equivalent to an abelian variety, then you are an abelian variety. And so together, these two things show the question has an affirmative answer. All right, it's also true for toric varieties. This is a more recent result by Cremona. I think maybe the most general positive result is by Anel and Towen. And they show that no matter what x is, the number of Fourier-Mukai partners is at most countable. So maybe not finite, but you can never have continuous families at least. OK, so the main thing I want to explain today is that actually the answer is no in general. And the counterexample is sort of a silly thing. You take x to be p3 blown up at 8 very general points. And the way this is going to work is, well, I mean, what are all the y's going to be? They're also going to be p3 blown up at 8 very general points. But the thing is, they're different configurations of 8 points. And so when you blow up 2 different configurations of 8 points, you get non-isomorphic threefolds, but they can be derived equivalent. So I guess precisely the statement I'm making here is if you fix a very general configuration of 8 points, there exist countably many other configurations of 8 points, such that the blow-ups are derived equivalent, but they're not isomorphic to the original one you started with. OK, so I'll explain how this goes. I'm not sure I can really kill a whole hour doing that, though. So I'm also going to explain how this same construction, more or less, gives you some other interesting counterexamples. So here's another question from a paper of Totaro. I think this one was not conjectured. Yes, it was more. It seems hard to find such a thing. But the question is, can you find a smooth projective variety? Well, and a Neff line bundle on that variety. Such that the set of curves on which L is 0 is countably infinite. Right? Usually if you have a Neff line bundle, you might think that if it's 0 on infinitely many curves, it's probably just because it's 0 on some curve that moves in an algebraic family, and so you get uncountably many. So the question is, can it be 0 on a countable set of curves? All right, and Totaro shows in dimension 2 that the answer is no. On a surface, if you have a Neff line bundle, the set of curves it's 0 on is either finite or it's uncountable when some such curve moves in a family. All right, the answer to this question, there is an example. So yes, we're going to take x to be, again, p3 blown up at 8 very general points. And the line bundle is, in fact, just the anti-canonical divisor. Actually, let me just point out sort of a funny corollary of this example. There actually exists a quasi-projective variety I'll call it U, for which the set of complete curves in it, so compact curves, is countably infinite. As far as I know, no one actually ever asked about this, but I think it's kind of fun to see an example. It's a very, very elementary question, but it's not so easy to actually write such a thing down. So we're going to have a quasi-projective variety with a discrete countable set of complete curves on X and no continuous families of curves. OK, so let me just tell you the construction now. And this is based on a very classical thing, just playing around with Cremona transformations. So let me start with sort of a warm-up in 2 dimensions, where maybe this is something you've thought about before. So let's just say we're in P2 and we have n points pi. And we have a curve in P2 of some known degree and some set of multiplicities at our points. So I'll call the degree d and the multiplicities mi. So I could pick 3 of my n points, and I could make a Cremona transformation centered at those points, meaning I blow up the 3 points, and then I blow back down the lines that go through any 2 of them. And after I do that, I get back to P2, and I can take the strict transform of the curve, and it will be some different curve. Right? Doing the Cremona transformation is going to change its degree and change its multiplicity. But it's easy to work out what are the degree and multiplicities of this strict transform. I think it's actually a problem in Hartshorne, so I won't do it now. But the new degree is going to be 2d minus the sum of the multiplicities at the 3 points where your transformation was centered. And the new multiplicities are going to be d minus the sum of the other 2 multiplicities of the points you were centered at. But there is something a little weird here, which is this. So say my curve, I had some configuration of points pi where I knew the multiplicities. After I do this Cremona transformation, the points move around. So for example, if 3 of my points here were collinear, not the ones where I made my Cremona transformation, but just 3 of the unrelated points were on a line, after you do the Cremona transformation, that's not true anymore. Right? If I had 3 collinear here, what will happen is over here I have 6 points on a conic. But it's a genuinely different configuration of points. So here's how I want to think about that. Given a configuration P of points, I'm going to write xp for the blow-up of P2 at those points. And what this Cremona transformation does, sorry. Oh, yeah, sure. So in P2, if I pick 3 points, I blow them up. And now between any 2 of those 3 points, there's a line in P2. When I blow up 2 points on that line, it goes from having self-intersection 1 to self-intersection -1. So then you're able to blow down the line between the points. And that's what the map is. You blow up 3 points, and then you blow them down. And the formula explicitly for the map from P2 to P2, if your 3 points are just the standard points 1, 0, 0, 0, 1, 0, 0, 0, 1, the map is just to invert each coordinate. But when my points aren't the standard points, I guess you can do a linear map to make them those points. Then you apply this. So the way I want to think about this is if I have a configuration P, I make a Cremona transformation at 3 of the points. I get a map. I mean, it induces a map between the blow-up at my original configuration and the blow-up at my new configuration. In dimension 2, this is an isomorphism. In higher dimensions, that's not going to be the case anymore. But not only that, this formula here tells me what the induced map on the numerical groups is. Right? A curve with degree d and multiplicities mi corresponds to a certain divisor class on the blow-up. And this formula is just telling us, with respect to this map, how do degrees and multiplicities change. OK, so I'm talking about blow-ups of P3, and we're going to need the Cremona transformation in P3. So let me say something about what that map is. So again, we can write it down using an explicit formula, and it's the same sort of thing. So it's the map P3 to P3 that inverts each coordinate. I don't know. This is not so enlightening. So let me tell you, how do you resolve this map? I mean, it's a toric map. So it's easy to figure out what the resolution is. So here's what you do. So in 2 dimensions, we blew up 3 points and then blew down stuff. We start the same way. So we blow up the 4 standard coordinate points. Sorry, this x and this x are are not the same. I'll never use this x again, I promise. OK, we blow up the 4 points. Now, between any two of my 4 points, there's a line in P3, right? It's a rational curve with normal bundle O1 plus O1. After I blow up 2 points on the line, its normal bundle drops to be O minus 1 plus O minus 1. And now you can flop this curve. Right, so there's 6 lines that go between 2 of the 4 points. They're the edges of a tetrahedron. Explicitly, what do I mean flop the 4 curves? Well, it's a rational curve with normal bundle minus 1, minus 1. You blow it up. You get an exceptional divisor that's P1 times P1. And then you blow that down in the other direction. So if you really want to resolve the map the whole way, you blow up the 6 lines and then contract the other way. OK, so you get this new thing, x prime. But it turns out that x prime, you can now go back down to P3. And what this map does is it contracts the 4 planes that go through 3 out of the 4 points, so the 4 faces of the tetrahedron here. So you take the strict transform of a plane in P3, and once you get to x prime, you can actually contract that divisor to a point. OK, so here x is a blow-up at 4 points. But if I had a configuration of more than 4 points, we get a map from xp, the blow up at all of the points. Right? I just take that x and blow up additional points, over to xq, which is p3 blown up at some different configuration of endpoints. Right, again, so this map from P3 to P3 downstairs is the Cremona transformation based at 4 out of my n points. And there's an induced map up above that just flops the 6 curves that go between 2 of the 4 points. But again, in general, P and Q here are not going to be isomorphic. For example, if 4 points of P are coplanar, that's not the case anymore on Q. I mean, they're genuinely different configurations of 8 points. OK, so maybe now you can start to guess how this is going to work. How we're going to construct these infinitely many varieties that are derived equivalent but not isomorphic.
You have to assume that the other points are not on those lines.
Yeah, that's right. So my points need to be fairly general for all of this to work. If I have 4 points coplanar, or one of the points on a line between the other 2, there's trouble. So the thing is, I don't want to say P is very general, because later on I'm going to require P to be slightly special. But you do need to take care that your Cremona transformations are always defined. So just think of P being general here. OK, so here's the game. Here's what we're going to do. We're going to start with P3 and fix a very general configuration of 8 points. And now if I pick 4 of those points, I can make a Cremona transformation centered at those. And I get a map to P3 blown up at some other configuration of 8 points. Now the map between the two things is just a flop. And a flop doesn't change the derived category. That's this Bondal-Orlov result. So xp and xq here are going to be 2 varieties that in general are not isomorphic, but that nevertheless have the same derived category. OK, that's 2 Fourier-Mukai partners, but we want countably many. But what you do is you keep going. So after you do this, you pick 4 points of Q, and you make a Cremona transformation centered at that. You get P3 blown up at some new configuration of 8 points. Right? So there's your third Fourier-Mukai partner. And you just keep going. You keep very cleverly choosing your 4 points. I mean, it's not that clever. It's classical, at least. But you carefully choose the 4 points to make a Cremona transformation at, and you get an infinite sequence of non-isomorphic varieties here. So there's basically 3 things we need to know to make this work. Right, the first is that if you blow up P3 at one configuration of points and you blow up P3 at a different configuration of points, they're not the same variety. Right? It's sort of believable. So if your configurations are not the same, I'm thinking of them as ordered configurations. So they have to be different up to Sn, just permuting them. Of course, also, if you just apply some automorphism of P3, the blow up at the two corresponding A tuples are the same. But if your two configurations are sort of genuinely different, then the blow-ups are not isomorphic. I don't know, this sort of sounds believable, but you really should think a little carefully here, because this is false in dimension 2. The thing is, if you blow up 6 points on a conic, you could blow down a different set of -1 curves on this surface, and you get back to P2, but you'll end up with 3 points on a line and 3 points not on the line. So in P2, this is false, but in P3, it's OK. I'll briefly say why. OK, the second thing you need to know is that if you can get from P to Q by a sequence of Cremona transformations, then they're derived equivalent. And this I've more or less explained already. It's because they're connected by flops. All right, and the third thing we need to check is that you actually do get infinitely many configurations this way. So if we're using at least 8 points, you don't just end up back where you started. Right, and of the 3 things, this is the one that has the most content, right? Somehow my proof needs to involve the number 8. If you try to do this with just 7 points and you keep picking 4 points, you're going to find you always end up back where you started. I mean, it's sort of related to the fact that P3 blown up at 7 points is a weak Fano variety, but at 8 points is not. I mean, maybe I should say, if you know the surface case well, P3 blown up at 8 points is kind of analogous to P2 blown up at 9 points. It's the one that's just past the Del Pezzo surfaces. So it's no longer a Mori dream space or anything good, really. OK, so let me just quickly say how these go. So for the first, well, here's what we do. So we have a map from P3 minus my 8 points to the blow up minus the exceptional divisors. If I have this hypothetical isomorphism from xp to xq, I can get a map to xq, and then I get a map back down to P3. And this is a map from P3 to P3 whose indeterminacy locus is 0-dimensional. It's just a finite set of points. Now, the inverse map has the same property. The map from P3 to xq to xp back to P3 is a map from P3 to itself whose indeterminacy is 0-dimensional. But it turns out if you have a map of P3 to itself with 0-dimensional indeterminacy locus, and the inverse also has 0-dimensional indeterminacy, it has to be an isomorphism. Someone told me this is proved by Zariski, but a recent reference is a paper by Kantah and Bayraktar. I mean, it's not so hard. You just think about what happens to the strict transform of an ample divisor. And this is the part that's not true in P2, right? The standard Cremona transformation from P2 to P2 has 0-dimensional indeterminacy both ways. But in P3, that's the difference. The Cremona transformation on P3 is undefined along these 6 lines. OK, for the second point, again, if P and Q are related by sequence of Cremona transformations, then we just have a sequence of maps between different blowups of P3 that starts at xp and eventually gets to xq. Each one of these maps just flops 6 curves. So to get from xp to xq, we flop a large number of curves, but every time you flop, it doesn't change the derived category. So xp and xq are derived equivalent. OK, so now for the third point. Right, so this one is the most annoying to check. And if you just think, I mean, how are you going to prove something like this? If you start with some very general configuration of 8 points, and you do a Cremona transformation, you get some new configuration of 8 points, but it's not really, I mean, what invariant are you going to use to tell them apart? And I mean, of course, it's easy to write down the map that this induces on the parameter space of 8 tuples of points, but then how do you check that this ugly rational map is not just finite order? So there's work to do here. And the trick is that instead of trying to deal with these parameter spaces and explicitly write down the rational maps, we're just going to choose our point P, the original one, to not be very general. We're going to make it so there's something special about this configuration. So we're going to choose P0 with the last 5 points, the last 4 points coplanar. And now the 4 points I pick, I mean, I'm not allowed to pick these 4 points as the center of my Cremona transformation. But if I pick some other 4 points from among the 8, there's no problem defining the Cremona map. And now here's what we do. We're going to define our n plus first configuration by making a Cremona transformation at the first 4 points of the nth. All right, then we can't just do the same thing again, right? If you do the Cremona transformation twice, you're back where you started. And the trick is that you do the Cremona transformation at the first 4 points, and then you reorder the points by moving the first one in your 8 tuple to the end of the list. You just cyclically permute them. And the claim is that if you choose P0 like this, and then you repeat this procedure, you get legitimately an infinite set of different configurations. And the reason is this. Well, we picked P0 to have a plane being 4 points on a plane. Now, P1 is not going to have 4 points on a plane, but there is something special about P1. The strict transform of the plane is an effective divisor, which is something you wouldn't get if your P1 were a very general configuration. So let's keep track of this like this. I'm going to make just a table of some divisor that we know to be effective. So right, so I picked my P0 to make a plane through points 5, 6, 7, and 8, an effective class. And again, this is a special condition that allows us to distinguish P0 from among all 8 tuples. Now, when I make a Cremona transformation centered at the first 4, there's some new effective class on the resulting thing. And you can work out the degrees and multiplicities and how they change under Cremona on P3, just like we did for P2. And what you end up with is, well, so the plane turns into a cubic hypersurface that has multiplicity 2 at the 4 points you centered the transformation at, and 1 at all the other points. And then I reorder them. So I get this. So that's what's special about XP1. It has there exists a cubic that's double at 4 of the 8 points and goes through the other 4 points. And for a general configuration of 8 points, that doesn't happen. This is a codimension 1 condition on configurations. And you keep going now. So we take P1 and we make a Cremona transformation, and we get a class that's effective on P2. I promise not to do too many of these. Yeah, so what's special about P2 is that there exists a quadric that has a double point at your 7th point and passes through all of the other points except P3. But here's the, again, this is a special condition. This doesn't hold for P0, but it does hold for P2. So we know P0 and P2 aren't the same. But here's the thing to realize, that going from each line to the next here, I'm just applying some linear map, right? I'm saying, here's how the degrees change, here's how the multiplicities change. So to get from here to here, you apply some matrix, right? It's the Cremona matrix and then a permutation to move the last point to the end. And what you find, well, here's the unenlightening proof. If you're using at least 8 points, this matrix is not idempotent. And in fact, this matrix has a 3 by 3 Jordan block with the eigenvalue 1. And the point is that now when you keep applying this matrix M and hitting this configuration, you get special divisors of higher and higher degrees. So if you type it into Mathematica, let me just do one example. When you get down to P100, you end up with there exists a degree 35 hypersurface that has 4 18-upal points and 4 17-upal points. But again, this is the existence of this effective class is a codimension 1 configuration on points. Right? This is, in general, not effective. But because I chose P0 to be special, it is effective. And so this is how you know that XP0 and XP100 are not the same thing. Right? Here I have some special effective class for coplanar. On P100, I have some special class, this highly singular degree 35 hypersurface. And the point is that once you have 8 points, the degrees of these go to infinity. And so these are all special in different ways, which means they're all not isomorphic. OK, I mean, that's it. So this shows that that example works. But let me make a few more remarks about both why this works and also some of the, I mean, oh, yeah, that's right. So you do need to do that. So to be really careful what you, yeah, sorry, I should have said this. You need to check that all of these conditions, only one of them holds if your points are general. And the trick to do that is you actually choose your P0 to all be on an elliptic curve. And then the plane being effective tells you that some particular combination of the points on the in pick 0 of the curve is 0, whereas in general it's not. Right? 4 on a plane is, I mean, you pick a type 2-2 curve in P3. The 4 points being on a plane means that if you take a plane, you restrict it to this degree 4 curve, and then you subtract P1 plus P2 plus P3 plus P4. That's 0 in pick of the curve. Whereas these will be some other combination of the points, and it won't be 0 in pick. So yeah, that's right. To be careful, you put the points on an elliptic curve, and then you can see that actually these are mutually exclusive. OK, so let me, I mean, this is not so enlightening. I didn't even tell you what the matrix M is. Here's how I think it's better to think about this example. So we have some space of 8 tuples of points up to PGL. Well, let's just say up to PGL. I mean, exactly what GIT quotient here you take doesn't really matter. And then there's some family over this such that the fiber over an 8 tuple of points in the base is P3 blown up at that configuration of 8 points. OK, so now making a Cremona transformation centered at the first 4 points induces a birational map of the configuration space. And the map doesn't change the derived type of the fiber, right? After you make a Cremona transformation, you get a new 8 tuple, but the corresponding blowups are derived equivalent. But you also have transpositions of 2 of the 8 points. Again, these are ordered 8 tuples, so this gives you another involution on the base. Right? If you exchange 2 points, of course, it doesn't even change the isomorphism type of the fiber. So we have a bunch of involutions acting on the base of this parameter space. And all of these involutions respect the derived type of the fiber. So I mean, together, these generate an action of some reflection group. I mean, in fact, it's a Weil group of some root system. But the thing is, I mean, there's criteria that will tell you if you have a reflection group and the generators satisfy certain relations, when does it become an infinite reflection group? And if you go through that stuff, you find that, well, 7 points, you're generating some Coxeter group. It's a finite Coxeter group. But once you hit 8 points and you have enough generators in this reflection group, it becomes an infinite reflection group. So I mean, that's the real reason that 8 is the magic number instead of 7. You get this infinite reflection group acting on the base. And again, I mean, this goofy procedure I'm doing here where I make a Cremona and then I permute the points somehow, this is just the product of all these generating reflections. And that's some infinite order element of this reflection group.
But then this heuristic implies that none should work too.
Oh, yeah. Any number more than 8 works OK. Yeah, it's just up to 7 that you have problems. Though for this other thing I said at the beginning, the Neff line bundle question, there it really is particular to 8. OK, I mean, are there any questions about the construction so far? Now I just want to make some remarks about the context where this comes from.
Does this last experience tell you that if you took very general points, this should still work? Or?
I mean, you still have to do something to check that even though it's an infinite group, you get infinite orbit of very general points. I think it's unavoidable to do some work. But at least it sort of explains why 8 is the number. So I think, let me just point out the two-dimensional version of this picture, because I think it's sort of fun too, even if not exactly relevant. So there you get some space of 9 tuples of points in P2. Some total space such that the fiber over a 9 tuple is P2 blown up at those 9 points. And what happens there is that if you have very general configuration P in the base, the set of Q's such that the blow-ups at the corresponding 9 points is Zariski dense. Right, so in 2-dimension, you don't get derived equivalence between things related by the Cremona transformation. They're actually isomorphic. So here you get a flat family of rational surfaces such that if you pick a point in the base, the set of other fibers that are isomorphic to it is a Zariski dense set, but it's not everything. I don't know. So if you didn't already believe there's no good moduli space for rational surfaces, I mean, there's another example that shows this. Oops. Well, let me switch to this board. So I should also say something about where else this transformation shows up. So as you'd guess, the action of Cremona transformations on configurations of points is a very old thing that was studied long ago. So I think the first sort of investigations were mostly in the case of P2 rather than P3, but the story is really not that different. So this was, I think, started by Cantor in the late 1800s. Duval later also does some things with this. I confess I don't really know who does what exactly. Then in the 20s, Coble really went to town on this stuff, and he has a whole book about essentially the action of the Cremona transformations on point configurations. Right, these I find extremely hard to read, so if you actually want to know about it, there's a book by Dolgachev and Ortland that discusses some of these classical results in a relatively comprehensible way. And I should say, I mean, it's hard for me to really say exactly what they proved in these, but at least the fact that the orbit of a general configuration of points in P2 is infinite is, I mean, it's explicit in Dolgachev's book, and probably you can extract it from Coble somehow. I mean, I don't claim any novelty in this proof. It really is an old argument here. OK, where else might you encounter this action? Well, I think these days it's something that people in complex dynamics know a lot about. And here's why. So what I proved is that if you pick a very general configuration of 8 points, and you keep repeating this procedure, you get infinitely many different configurations of 8 points. On the other hand, if you choose your initial P0 very, very carefully, it could turn out that P1 is the same as P0, and that all the Pn's are the same. So what would that mean? I mean, I did all this work to show that this doesn't happen very generally, but in fact, it can happen. This is an extremely high codimension condition on configurations, but they do exist. So here's how this shows up. In dimension 2, if you do this and you get back the same configuration, you get a map from x blown up at this configuration to 0, p0, to x blown up at p0. It's an automorphism of a single surface. We get a map from the thing to itself. So explicitly, what's going on is that a map from P2 to itself that's a Cremona transformation composed with some linear map. Down here, it's just a rational map. But when you blow up this extremely carefully chosen configuration P0, you actually get an automorphism. And again, it's very hard to find a linear map in a configuration P0 such that it happens. But it can. So in dimension 2, well, I think this is about 10 years ago. It was worked out by McMullen, and then in sort of different language, but doing the same thing by Bedford and Kim. And what you get is it's an infinite order automorphism of this surface, and it's an automorphism that has very interesting dynamics. It has, well, if you use 10 points instead of 9 in P2, it's a positive entropy automorphism. Where entropy here is exactly this thing in dynamics about separating the orbits of sufficiently general points. And McMullen shows that this map you get from these fixed points of the Cremona action really does have some sort of novel dynamical properties even about, well, there are Ziegel disks and all sorts of strange things you can read about. More recently, people have been looking at this dynamical stuff in higher dimensions, and it turns out that such configurations P0 always exist. Here, so this is by Peroni and Zhang. And then again, sort of in parallel, by Bedford, Diller, and Kim. Oh, yeah, sorry. And in dimension 3, you don't get a regular map. You get a map from the thing to itself with one-dimensional indeterminacy. So it's what's called a pseudo-automorphism. So again, this is this very special thing when P0 is the same in P1. But for our example about derived categories, that's exactly what you want to avoid. And if you pick very general points, there's no problem. OK, let me see if there's any other things I wanted to mention here. Oh, yeah, well, I think every time I talked about this, I get asked the same question. So let me head it off right now. If you want, you can get all of the XPNs to be defined over Q. No, finite fields, you're in trouble because of the. I mean, I don't know about countable fields in positive characteristic. Well, it's an interesting question. I mean, people study the Cremona action in positive characteristic, and there's a lot of interesting questions there, which I don't know anything about. But the way that you check this is, again, the way you need your points to be very general is something about independence of the points in the group law of some elliptic curve. If you choose your curve to be over Q and if its group of rational points is rank 2 is enough, probably rank 1 is enough, then everything is OK. OK, I have just a couple more minutes. So let me say something about this line bundle that's Neff, but 0 on many curves. I mean, any question about the construction so far? All right. Yeah, that's an interesting question I don't know about. So, I mean, it's easy to write down exactly what kind of map you get between these things. You just resolve the Cremona transformation. To be honest, I know basically nothing about derived categories. And so I don't know even if this explicit flop gives a derived equivalence. But maybe someone here has an idea. All right, surely it should, says the audience. Yeah, I don't know, but yeah, almost everything goes through exactly the same in higher dimensions. OK, so let me say something about this second example. Oh, I should have said at the beginning. This stuff I worked out with John Autumn. And again, the claim here is that we can take X to be the same variety we've already been talking about, and we can take L to be the anti-canonical divisor. And let me actually work with the anti-canonical divisor over 2, just because it's divisible by 2, and I'll inevitably forget about that. OK, but on P3 blown up at 8 points, the canonical class is minus 4h plus 2 times the sum of the exceptional divisors. So this divisor we're looking at here is 2h minus the sum of all the exceptionals. In other words, this is the linear system of quadrics going through the 8 points. So let's just think a little as a sanity check about, is it plausible that this thing works? So first, why is L even Neff at all? Well, there's a very simple reason for this. So there's a 9-dimensional space of quadrics in P3. If you impose that your quadric goes through 8 points, you're left with a pencil. So if a divisor moves in a pencil, what curves could it possibly be negative on? It's the curves in the base locus, right? So the only thing we need to check to know that this divisor is Neff is that it's non-negative on every curve in its base locus. Well, its base locus is a single curve. It's just the intersection of any 2 quadrics in the pencil, which is a degree 4 curve of genus 1. So I'm going to write Q's for things in the pencil. Again, a Q is a quadric through the 8 points. Well, so to know its Neff, we just need to compute L dot B. But L dot B is going to be 2 times 4, 8, and then minus 1, 8 times, so it's 0. OK, so this divisor is definitely Neff. What about curves that it's 0 on? Well, just at first glance, it's easy to find some curves it's 0 on. So for example, if I take a line through 2 of my 8 points, that's a curve in the class h minus e1 minus e2 or whatever. But L dot that line is 0. I could take a twisted cubic through 6 of my 8 points. And if I take a twisted cubic and intersect with L, what do I get? I get 2 times 3 and then minus 6 times 1. So 0 again. OK, so this, I think, is 50-some points that it's 0 on, right? The lines through any 2, the twisted cubics through any 6, and also the base locus. So if nothing else, this is a Neff divisor that's 0 on quite a few curves. Now, to finish proving the theorem, there's really 2 things I need to check. I need to check, A, that there are, in fact, infinitely many curves that it's 0 on, and B, that there aren't uncountably many curves. Somehow I need to show that there are at most countably many. And I'm going to prove these 2 things more or less separately. OK, so here's where the infinitely many curves come from. These things we more or less constructed already. So remember that before we got an infinite sequence of flops. Let me actually this way do the Cremona transformations in, going off in the other way. But say I took a line through 2 points on xp3. Right? So this is a rational curve of normal bundle O minus 1 plus O minus 1. If you take its strict transform under all these flops, you again get a rational curve here with normal bundle O minus 1 plus O minus 1. I mean, there's something to check here. You need to check that this curve never meets the indeterminacy locus of any of these flops. But it's true, it doesn't. So if I take a line between 2 points on xp3 and I take its strict transform, I get a rational curve with normal bundle O minus 1 plus O minus 1, but of quite large degree. That's the good news. So if I took a line through 2 points on x100 and I took its strict transform under 100 flops, you end up with a curve here with degree, well, I don't know, 30 or something, but a rational curve of that normal bundle in high degree. And if you go further and further back, of course, you're going to get countably many curves. You know they're different because their degrees are unbounded. Right? I should say a rational curve with normal bundle O minus 1 plus O minus 1 is always kx trivial. So these are all curves that L is 0 on. So how do I know I didn't miss any curves? I mean, I gave countably many, but maybe there's just some obvious family and it's 0 on all of them. But the trick here is that L moves in a pencil, and we can use that to show that that doesn't happen. So let's just say I have just any curve on this threefold. Now I can just pick a point on that curve, right? And because L moves in a pencil, that point is on some element of the pencil. So how could it be that C dot L is 0 if C meets an element of the pencil for sure? Well, it must be that C is contained in Qt. So to figure out what curves L is 0 on, we just need to understand which curves in the quadrix Qt is it 0 on. But if you restrict L to Qt, well, remember, L is quadrix through the 8 points, so the restriction is a divisor of class 2, 2 on this quadric Qt. And it's, in fact, anti-canonical. Yeah. So what we have is a rational surface, well, a family of rational surfaces, Qt. And I want to understand, in that family, when does it happen that there's a curve that the anti-canonical is 0 on? All right, and I won't go through all of this in detail, but if you have a rational surface with an effective anti-canonical, the only way it can be 0 on a curve is if the curve is a -2 curve. And this is basically just adjunction. It's easy. So the question now, what curves could L be 0 on? Well, it's exactly the -2 curves that appear as these quadrics move in a pencil. The good news is, though, that for a very general member of the pencil, there are no -2 curves whatsoever. So for very general Qt, L is not 0 on anything. But whenever you have a family of rational surfaces, it typically happens countably many times that a -2 curve appears. It can't be more than countably many. So there's at most countably many times in the family that a -2 curve appears. And so there's at most countably many curves with L dot z equals 0. OK, and that's it. So we explicitly constructed infinitely many rational curves. And there can't be any more than that, because they all have to be -2 curves on members of the pencil of quadrics. And this happens at most countably many times. Well, maybe just a funny remark here. The other construction is fine if you use P3 blown up at more than 8 points. But here we actually don't know a single example on Pn blown up at k points for any values other than P3 blown up at 8 points. It really is very specific here. If you take P3 blown up at more points, the anti-canonical is not nef anymore. If you take P4 blown up at points, I mean the anti-canonical is already not nef as soon as you blow up 2 points. So this construction is really specific to the 8-point blow up of P3. And I guess I'll leave it at that. Thanks.